Hello and welcome to the lecture series on Total Quality Management. I am Dr. Vinod Kumar Yadav from the Department of Mechanical Engineering, GL Bajaj Institute, Greater Noida. Today we'll cover the part reliability, its evaluation and measures. So before starting that, we must discuss what's the difference between quality and reliability. Basically, we have defined that the quality is conformance to the specification. If a component meets the required specification or planned specification that is being set by the manufacturer, then it obeys the requirement of the quality or meets the quality requirement. So it confirms it. So we can say that quality refers to the conformance to specifications, whereas the reliability deals with the life period or lifetime. So reliability is basically how well the product maintains its original level of quality over time. That is, we have specified some time limit or lifetime of a particular product, and reliability defines if it meets the lifetime requirement and maintains the same quality, right? So some ways of improving the reliability are by using the proven design that is already valid. We can use a safer design, we can use the simple designs. So by this way we can improve the reliability of the product, and by proper testing before use this may be improved. By using some standby parts or redundant parts in high risk areas where chances of failures are more. So by using components in parallel, as we have discussed in part 1 of this reliability series lecture, in which we have discussed that two main reliability block diagrams are used. One is series connection, other is parallel connection, or there may be a combination of series as well as parallel. So we have seen that in parallel connection or parallel reliability diagram, the reliability is more because that is not a productive outcome. So but in case of series connection, the reliability is less due to productivity analysis. So by using proven manufacturing methods, we can improve the reliability. So these are some parameters by controlling which we can improve the reliability of the product. So we'll also discuss the maintainability because some components are maintainable. So as we know that maintaining means to bring back to the product into original condition. So that maintainability may be defined as the probability that a failed item will be restored to operational effectiveness within a given period of time when the repair action is performed in accordance with the specified procedures, right? So maintainability is basically deals with the products which are maintainable in nature. Some products are not maintainable. Okay, like for we talk about the car's battery, that is maintainable. If one of the cells of the battery becomes faulty or damaged, then this may be replaced. But if you talk about the battery or cell of a torch, that torch is not that battery is not repairable. That has to be thrown off if it is not working properly. Okay, so second parameter is availability. So availability is basically the proportion of time for which an item is not failed. That basically deals with the proportion of time for which the item is operative without any failure. So we can use the unavailability term also. Okay, that is 1 minus availability. This can also be used. So the most important part of product's life is the life history curve. That is very important to describe the behavior of the part, how it fails with the passage of time. So this curve basically is drawn between failure rate and time, in which the on x-axis the time is plotted, on y-axis failure rate is plotted. So this curve has basically three phases, and this curve is applicable to an infinite number of items. This has been plotted on the basis of the results obtained from an infinable number of items. So this is applicable generally to almost all the items, and the three phases of the life history curve includes the debugging phase, chance failure phase, and wear out phase. This life curve basically, in these curves, the probability distributions as indicated in this figure number 2 can be used to describe the three phases of the bathtub curve. So as we have discussed in last lecture, this is our Weibull distribution curve. So here we can see that in first phase of debugging, the rate of failure may be disc described by this particular graph, this curve, which represents the shape factor or slope of 0.5, that is beta. Beta is 0.5. So when beta is 0.5, this curve may be used to describe the failure rate in phase number 1, that is debugging phase. Okay. Similarly, if beta is equal to 1 in case of Weibull distribution, the failure rate can be assumed to be a horizontal line like this. So second phase of the bathtub curve or life history curve, this part is similarly like a horizontal line when beta is equal to 1, as in this curve. This is for Weibull distribution. So if we see the third phase, that phase is being replaced by, or maybe analogous to this phase, representing beta's value as 3.5. Here the shape factor is 3.5 or slope is 3.5. So by substituting this shape factor's value as 3.5, we can predict the rate of failure in this case, which is a sharper rise with time. So that's why I have said that probability distributions are used to describe the three phases of bathtub curve. So we'll discuss in detail now. The phase 1 is also known as the burn-in phase or infant mortality phase. Okay, so this is basically marginal and short life parts that cause a rapid decrease in failure rate lie under this phase 1. Okay, so if we talk about the Weibull distribution curve, the shape parameters that we have discussed here in this slide, the value of beta is less than 1. Okay, less than 1. So here Weibull distribution curve, when the shape factor's value is, that is beta is less than 1, is used to describe the occurrence of failures. Okay, to describe this curve. Okay, for some of the products this may be treated as a testing phase, or some of the products may be a warranty phase. Okay, so this phase is the initial phase in which debugging is there, and generally the rate of failures are rapidly decreasing, okay, with the passage of time. If we talk about the second phase, then that is known as chance failure phase. Okay, so as we have discussed here, the Weibull distribution shape factor beta is equal to 1. So normally we have plotted it for infinite number of components. So this seems to be a horizontal line, okay, where the failure rate is approximately constant. Okay, so few products may not follow this particular line, and they may, the failure rate may decrease like this or may increase like this. So these are few in number. So in general, the horizontal curve is being accepted and adopted and is observed for a infinite number of items. Okay, so the exponential distribution and the Weibull distribution shape, where beta's value is 1, may be used to describe this phase of the life history. Okay, uh, we can assume for exponential as well as for Weibull distribution the value of shape factor to be 1, and can compute the failure rate for this phase. We'll see today the examples of computation of failure rates also under different conditions and under different failure rates. So the phase third is known as wear out phase. Here the wear is obvious because the product has met its life cycles requirement. So this may be wearing, and we can see a sharp rise in the curve. Okay, so the failure rate sharply rises in this zone. So for this curve, the rate of failure may be best described by normal distribution curve. So Weibull distribution curve may also be used when value of beta is more than 1. As you have seen here, this beta's value is 3.5. So when its value is more than 1, so it sharply increases, and when it becomes beta 3.4, then with beta 3.4, the Weibull distribution will be exactly similar to normal distribution. Okay, so this may be, we can use the normal distribution or Weibull distribution for carrying or conducting or calculating the wear out analysis or computing the wear out failure rate. Okay, we'll see with an example. So basically in life history curves, every product passes through these three life curves, which are plotted for infinite number of components. The first phase is debugging phase. Second phase is chance failure phase, which is horizontal line. The failure rate approximately remains constant. Third phase is wear out phase, where the failure rate rises sharply with the passage of time. So these are the three phases. Then we'll do with a normal distribution analysis. We have to find out the rate of failure by assuming that the failure is normally distributed. Okay. For this analysis, for normal failure analysis, we used to calculate the reliability of the product using this expression, that is 1 minus this integration of 0 to t ft dt, where, as we have discussed, this parameter 0 to 2 ft dt is basically showing the area under the curve. Okay, so this shows the area under the normal distribution curve. So we have certain tables, standard tables are found inside the textbooks at the ends, through which we can directly compute the value of this particular parameter, that is probability of this part. So this area under the curve can be computed using these tables. Okay, so we'll take an example. So this reliability is equal to 1 minus this parameter, and this parameter is equal to 0 to t ft dt. So we'll see an example. An ignition lighter that is used in kitchens has a mean life of 1000 hours and standard deviation of 500 hours. Calculate the reliability at 1500 hours. So we have seen here that the given parameter is the value of mu or theta. Mean life is 1000 hours. This is corresponding to theta or mu. Okay, the mean life. Okay, then standard deviation is 500, that is sigma is 500. Then we have to find out the reliability at 1500 hours. So this is mean value. So we have tested say 10,000 samples, and out of which we have found that the mean value is 1000 hours. So we have to compute that at 1500 hours what is the reliability of the product, of almost all the products. So we assumed here that it follows a normal distribution. Okay, and by assuming this expression, normal distribution, the value of z can be found as x minus theta upon sigma. So this parameter is plotted, is shown here in this table. Okay, x minus mu upon theta, or x minus theta upon x minus mu upon sigma, or x minus theta upon sigma, that is basically the mean value. So this is plotted here. At 1.0 we have seen that this value comes out to be 1.0. At 1.0 this is 1.00. At 1.0 the value is 0.8413. So we can find out the reliability at this parameter, at this value. Reliability at 1500 hours will be equal to 1 minus this value. This comes out to be 0.1587 or 15.87%. Hence we can say that 1587 products out of 10,000 lighters will last in 1500 hours. So this was the computation for normal failure analysis. Now for exponential failure analysis, we can find out the expression as RT equal to e to the power minus t by theta. So exponential distribution and the Weibull distribution are used to describe the constant failure rate. So reliability can be determined using this formula. So where t is the time or cycles and theta is the mean life. So how to use it? Say take an example. Calculate the reliability of a product at t, that is time or cycles, is equal to 50 hours, 60 hours and 70 hours. The mean life or MTTF for a constant failure rate was 60 hours. So using this expression we can find out the reliability at 50 hours, 60 hours and 70 hours. So just substitute these values in these expressions. So this will be, first part will be exponential minus 50 divided by mean value, that is 60. So minus 50 by 60, we can compute that e to the power minus 5 by 6. So this comes out to be 0.434. When we substitute 60 here in this expression, then this will be 60 by 60. So it will become exponential minus 1. So this will be 0.367. And similarly for 70 hours we can compute the value as 0.311. So here we can observe that with the reliability decreases with passage of time. As the time increases, the reliability decreases. So this was an observation with exponential failure analysis. So exponential failure can be judged using this expression and by using this technique. So third failure analysis is done by approximating the failure rate as Weibull as it follows the Weibull distribution. So Weibull distribution can be used for any of the three phases of the bathtub curve, as we have discussed earlier during the bathtub curve analysis, with beta equal to 1, beta less than 1, or beta more than 1. Here we have discussed it. So for this, because here beta is less than 1, here beta is equal to 1, here beta is more than 1. So this Weibull distribution curve is feasible for all the three phases of the bathtub curve. So beta equal to 1, Weibull approximation is becomes analogous to exponential distribution. Okay, and if, as I have told, if beta equal to 3.4, then this Weibull approximation will turn out to be normal distribution. Okay, so for this Weibull analysis, we have an expression. This is the expression for exponential failure analysis. We can find out the reliability by using the Weibull distribution approximation. So this will be equal to e to the power minus t by theta, this one, to the power beta. So this can be used to compute the reliability. So where beta is the Weibull slope, beta and theta can be determined graphically or analytically. We have certain tools to find out the graph or graphically or analytical value of beta. So I have indicated here power that this was not able to visualize in this PowerPoint, because this beta seems to be in multiplication, but this is in power. So I have indicated here this is power minus t by theta to the power beta. So this is the parameter. So we can see with an example, the failure pattern of a product follows the Weibull distribution with slope of 3.8. This beta is 3.8. Okay, and this is not following a normal distribution as the value of beta is more than 3.4, and mean life of 90 hours, that is theta is 90 hours, determine its reliability at 100 hours. So we want to compute the reliability at 100 hours. So this expression will become e to the power minus 100 by 90 mean value to the power 3.8. When computed, this will give as 0.224. So these expressions are used to analyze the failure when the failure seems to be normally distributed, when it is an exponential failure, or a Weibull failure. So as we have seen that Weibull can be used for any phase of the bathtub curve. So we'll see how the reliability is measured. So basically there are three important parameters through which we can measure the reliability. The first parameter is mean time between failures, that is also in short known as MTBF. The second parameter is mean time to failure, that is known as MTTF. And third parameter is mean time to repair, okay, that is MTTR. So mean time between failures, the components which have the probability of repairing, they for that also we can, that only we can compute the mean time between failures, MTBF. So this is applicable only for repairable product. As we talk about the car's battery, it is repairable, so it can be repaired. So we can analyze the MTBF analysis to compute the lifetime or mean time between failures. So we can say that how reliable a product is indicates the mean time between failures, okay, indicated by this parameter. So this is measured in thousands, as we have seen with the example of 10,000s of hours between failures. So this may be represented as the ratio of total operational time to the total number of failures. Okay, this is applicable to an infinite number of component for which we have computed, we have observed, we have measured the data and recorded it and computed this parameter. So this seems to be total operational time of all the components and number of failures that had occurred. So this will give a mean value. So this may also be written as available time upon number of failures. This total operational time is basically the actual available time for which the component is operative and divided by number of failures. So this available time is basically planned time minus downtime. Downtime is the time duration which it is faulty or the product is idle, okay, during maintenance phase. So this is the difference between planned time and downtime. Say we have planned that this particular component will work for 70 hours, but for during 70 hours it was inoperative for 2 hours due to some problem. So the available time will be equal to planned time minus downtime. So here we can replace this parameter as planned time minus downtime upon number of failures. So basically what we can say, the MTBF basically measures the availability and reliability. Here we can check that up to how much time the product is available and how it is reliable, how much it is reliable. Okay. So we can say that higher the value of MTBF, more reliable the product is. So to get a reliable product, the MTBF should be as high as possible. So the second parameter is mean time to failure, MTTF, and this is applicable to non-repairable products. Okay, this is not applicable to repairable products. As I have quoted an example that the cell of a battery, the cell of a remote or cell of a torch is non-repairable. It cannot be repaired. It has to be replaced. So this is applicable to that sort of product. So where the maintenance metric that measures the average amount of time a non-repairable component operates before its failure. Okay. So before failure, it will operate suitably. It's the average lifetime of an asset that is irreparable, as I have told at the beginning. So it's basically the lifetime of any product or service, okay, that is irreparable. So MTTF may be referred as the ratio of total operational time during which it was operative to the number of units under test. Okay, so that is performed for a, a, a huge or a large number of products. So that is calculating the mean value, okay, for a large number of products. So it is basically the ratio of total operational time upon number of units under test. The third parameter applicable to repairable product is mean time to repair. So it refers to the amount of time required to repair a system and restore or bring back it to final initial condition or fully functional condition. Okay, so this may be written as MTTR, that is mean time to repair, is equal to the ratio of total maintenance time to the number of failures. Okay, how much maintenance time it requires and during which how much failure was occurred. So this MTTR is equal to downtime upon number of failures. So this measures the availability of the product. Okay. So this availability, as we have discussed, is MTBF, mean time between failure, upon MTBF plus MTTR in percentage. So we can also compute the reliability using this parameter. So this is the last part, and these are the references.